Sometime in the last few weeks, inside a control room at NASA's Jet Propulsion Laboratory, a small team of engineers made one of the highest stakes decisions in the entire history of the Voyager mission. And right now, there is no public confirmation of how it turned out, not because NASA is hiding anything, because the spacecraft involved is currently more than 13 billion miles from Earth, and even a simple yes or no answer takes nearly 20 hours just to travel home. There is no dashboard anyone can refresh, no live feed, no press conference scheduled in advance, because nobody on the ground actually knows what the spacecraft will report until the spacecraft itself has already decided, hours or days earlier, out in the cold and the dark, whether the plan worked. This is the story of what NASA is calling, quite literally, the Big Bang, a last-ditch engineering gamble to keep two of humanity's oldest working machines alive a little longer, and why the decision happening right now, in the summer of 2026, might determine how much more the most distant spacecraft in human history ever get to tell us. To understand why NASA is taking this kind of risk with hardware, nearly 50 years old, you have to understand exactly how precarious things have gotten for Voyager 1 and Voyager 2. Both spacecraft launched in 1977, Voyager 2 first, on August 20th, followed by Voyager 1 on September 5th. Both completed their original missions decades ago, flying past Jupiter and Saturn, with Voyager 2 alone continuing on to also become the only spacecraft in history to visit Uranus and Neptune. Both then kept going, becoming the first two human-made objects to ever cross into interstellar space, Voyager 1 in 2012 and Voyager 2 in 2018. And both are still out there right now, still transmitting, powered by radioisotope thermoelectric generators, devices that convert the heat given off by decaying plutonium into electricity. At launch, each spacecraft's generators produced roughly 470 watts. Today, nearly 50 years later, that output has fallen dramatically, and it keeps falling permanently at a rate of about 4 watts every single year, with absolutely no way to reverse it, no way to refuel it, and no way to send a repair crew across billions of miles of empty space to fix it. For years, the strategy for managing that decline has been straightforward, if painful. As available power drops, mission engineers shut off instruments, one at a time, in whatever order preserves the most scientific value for the longest possible time. Of the 10 scientific instruments each spacecraft originally carried, most have already gone silent. For years, the strategy for managing that decline has been straightforward, if painful. As available power drops, mission engineers shut off instruments, one at a time, in whatever order preserves the most scientific value for the longest possible time. Of the 10 scientific instruments each spacecraft originally carried, most have already gone silent. The cameras on both spacecraft were switched off decades ago, not long after the Neptune encounter in 1989, since there was nothing left to photograph in the featureless dark of interstellar space. Instruments studying ultraviolet light and planetary radio emissions, built specifically for the close planetary flybys of the 1980s, were retired one by one in the years that followed, their scientific usefulness having ended the moment the spacecraft left the planets behind. What remained, heading into this decade, was a small handful of instruments built specifically to characterize the deep, cold environment of interstellar space itself, tools that only became truly valuable once each spacecraft actually crossed the heliopause and started sending back data from somewhere nobody had ever measured before. And then, on April 17th of this year, engineers at JPL sent the command to shut down Voyager 1's low-energy charged particles, an experiment known as LECP, an instrument that had been running almost continuously since 1977, measuring the ions, electrons, and cosmic rays surrounding the spacecraft for nearly 49 straight years. It was the same instrument that had already been switched off on Voyager 2 back in March of 2025. LECP was not just another sensor. It was one of the key instruments that had helped scientists determine exactly when and where each Voyager actually crossed the heliopause, the boundary separating our sun's influence from true interstellar space. Losing it meant losing one of the last direct, in-place tools for understanding the region. Both spacecraft are currently flying through, a region no other instrument humanity has ever built has ever occupied. The decision to shut LECP off did not come out of a calm, scheduled rotation either. It came out of a scare. During a routine roll maneuver on February 27th of this year, a standard operation Voyager 1 performs periodically to calibrate its magnetometer. The mission team noticed something they had not expected. The spacecraft's power levels dropped suddenly and sharply. Had that drop continued even a little further, it would have triggered an automatic fail-safe system on board called undervoltage fault protection, a system designed to protect the spacecraft by shutting down components on its own the moment power gets dangerously low. Recovering from an automatic shutdown like that, on a machine nearly half a century old, sitting more than 15 billion miles from the nearest engineer, would have been an enormously risky and uncertain process, with no guarantee of success. Shutting down LECP deliberately on their own terms was the team's way of getting ahead of a crisis before the spacecraft's own safety systems forced their hand. But shutting off one more instrument only buys time. It does not solve the underlying problem, which is that both spacecraft are quite simply running out of electricity permanently with nothing anyone can do to add more. This would not be the first time this exact team has pulled off something that sounded, going in, close to impossible. In 2023, Voyager 1 began transmitting nothing but garbled, unreadable data for nearly 5 months, the result of a single memory chip inside its flight data system that had physically degraded after nearly 5 decades of exposure to cosmic radiation. With no way to send a repair crew, and every single diagnostic exchange requiring a minimum wait of close to 2 full days round trip, engineers spent months slowly, patiently working out that the corrupted section of code could not be fixed in place, but could be split apart and relocated to other working memory elsewhere on the spacecraft. It worked. Voyager 1 came back online in 2024, still transmitting real science data from interstellar space. That history matters here, because it is part of why the team is willing to attempt something as inherently risky as the Big Bang now. They have already proven, more than once, that patient, methodical engineering can pull this exact spacecraft back from the edge of permanent silence. Which is where the Big Bang comes in. The idea behind the Big Bang is almost deceptively simple to describe, even though executing it on hardware this old, this far away, carries real risk. Each spacecraft currently uses a set of heaters to keep the propellant lines feeding its small maneuvering thrusters warm enough that the fuel inside does not freeze solid, a real danger in an environment this cold, this far from any source of heat besides the spacecraft's own dwindling generators. The Big Bang plan calls for switching off 3 of those existing heater devices all at once and simultaneously, switching on 3 different lower power devices designed to keep those same fuel lines warm using meaningfully less electricity, something on the order of 10 fewer watts of total power draw. If it works exactly as intended, the maneuver would free up enough power to delay the next scheduled instrument shutdown on each spacecraft by at least a year. And in a best-case scenario, there is even a chance it could free up enough electricity to switch Voyager 1's newly silenced LECP instrument back on. Engineers have reportedly kept a small half-watt motor associated with LECP running specifically in case that becomes possible, rather than fully decommissioning it. It is called the Big Bang because of how it happens, not because of anything about its scale in absolute terms. Unlike the slow, one instrument at a time approach the mission has used for years, this is a coordinated swap of multiple systems, several devices going dark and several different devices lighting up, all within the same operation, on a single spacecraft at the same time. On hardware, this old changing several things simultaneously instead of one small step at a time is inherently riskier, because there is less room to observe the effect of any single change before moving to the next, and because an unexpected interaction between systems could, what was in the worst case, leave the spacecraft's fuel lines without adequate heating even briefly, a problem that could cause permanent damage in an environment this cold. Propellant that freezes inside a fuel line on a spacecraft 15 billion miles away is not a problem any engineer can walk out and thaw by hand. It would very likely mean losing the ability to keep the spacecraft's antenna precisely pointed at Earth at all, which would functionally end the mission, regardless of how much power remained in the generators, because a spacecraft that cannot aim its own signal at our planet cannot tell us anything, no matter how much science it might still be capable of collecting. Given those stakes, NASA chose to run the experiment first on the spacecraft with the better odds. Voyager 2 currently has slightly more power margin to work with than its twin, and it also sits closer to Earth, meaning any commands sent to it and any data sent back in response travel a shorter distance and take less time. Both of those factors make Voyager 2 the safer test subject for a maneuver. Nobody has ever attempted before on hardware this old. NASA scheduled the Big Bang tests on Voyager 2 for May and June of this year. If those tests succeeded, the plan was to attempt the same maneuver on Voyager 1, no earlier than July this month, right now on a spacecraft currently sitting more than 16 billion miles from Earth, where a single round-trip communication with the ground takes somewhere close to 2 full days to complete. That is where the story currently stands. As of now, there's been no widely reported public confirmation of exactly how Voyager 2's test went, or whether the attempt on Voyager 1 has already begun, is currently underway, or is still being prepared. That is not a gap in reporting so much as it is a reflection of how this kind of deep space engineering actually works. A test like this does not resolve in an afternoon. Engineers send a sequence of commands, wait the better part of a day for confirmation that it reached the spacecraft, wait again for telemetry showing what actually happened, and only then decide on the next step, evaluating results with the same patience the mission has required for nearly 5 decades. Whatever the outcome, the decision happening around this exact moment is one of the most consequential the Voyager team has faced in years, because it will help determine whether Voyager 1's LECP instrument, one of the last tools we have for directly sensing the structure of interstellar space around it, gets a second chance to operate, or stays silent for good. It helps to understand what would actually be lost if that instrument never comes back. LECP was one of the primary tools scientists used to characterize the plasma and particle environment during each spacecraft's crossing into interstellar space, work that helped confirm the boundary had actually been crossed and helped describe what conditions on the far side of it actually looked like. A researcher who has worked directly with the instrument at the Johns Hopkins Applied Physics Laboratory has described its measurements as central to understanding both cosmic rays and solar particles, and to sensing the specific moment each spacecraft moved from the influence of our sun into the space beyond it. Without it, scientists studying the region Voyager 1 is currently moving through are left relying on whatever remains of its other instruments, and once those go dark too, the loss becomes permanent in every meaningful sense, because no other mission currently exists, or is even funded, that will reach interstellar space again for decades, if ever. That last point is worth sitting with, because it is easy to read past it. There is no Voyager 3 waiting in a hangar somewhere. There is no faster spacecraft on the drawing board, designed to catch up to either probe and take over its work. Every single measurement either Voyager makes from this point forward is, for the foreseeable future, the only measurement of its kind that our species has access to. A new mission built today, launched today, using the fastest propulsion currently available, would still take decades just to reach the distance Voyager 1 and Voyager 2 already occupy. And that assumes such a mission gets funded and approved in the first place, which, as of now, it has not. Whatever data these two aging spacecraft manage to send back between now and whenever their power finally runs out entirely is not simply valuable. It is functionally irreplaceable on any timescale that matters to the scientists currently working on this data, or very likely to the scientists who train under them. Both spacecraft are already down to the smallest sets of active instruments in their entire near 50-year history. Voyager 1 currently has only two functioning science instruments left, its magnetometer and its plasma wave subsystem, following the April shutdown of LECP. Voyager 2 is not far behind. Its own plasma science instrument was switched off back in October 2024 to conserve power, and mission plans call for its cosmic ray subsystem to be shut down sometime this year as well, which would leave it, too, with only two instruments running, the same two remaining active on its twin. After that point, the list of decisions left to make grows very short. Engineers will eventually have to choose which of those final two instruments to keep on each spacecraft, and for how long, before both Voyagers are reduced to sending back nothing but basic engineering telemetry, confirmation that they are still alive and still transmitting, with no science data attached at all. There is no way to overstate how final each of these choices actually is. Every instrument that gets switched off on these two spacecraft is being switched off by a team of engineers sitting on Earth, sending a command that will not even arrive for the better part of a day, with full knowledge that in almost every case, there is no way to reverse the decision later. That is precisely what makes the gamble behind the Big Bang so unusual. It is not simply another item in the long list of shutdowns the mission has carried out for years. It is an attempt to claw back power that has already been spent. To reverse, even partially, a decision that under normal circumstances would have been permanent on a spacecraft that has been in continuous operation in one of the most hostile environments humans have ever placed hardware for nearly half a century. And even as this decision plays out, the mission keeps adding to its own list of records. Voyager 1 is projected to reach a distance of exactly 1 light day from Earth in November of this year, a symbolic threshold, meaning a radio signal moving at the literal speed of light will need a full 24 hours just to complete the one-way trip between the spacecraft and mission control. No human-made object has ever been that far away while still transmitting. Send a command on a Monday, and you would not know whether it even arrived until Tuesday, and you would not hear back whether it worked until Wednesday. It will keep moving outward regardless of what happens with the Big Bang, regardless of how many instruments remain switched on, carrying its golden record and its faint signal deeper into the same interstellar dark. Its twin has been studying since 2018 at a speed of roughly 38,000 miles an hour, adding tens of thousands of miles to that distance with every hour that passes, whether anyone on Earth is watching or not. What makes this particular moment worth paying attention to right now is that it is genuinely unresolved. This is not a story with a tidy ending already written, the way so many space stories are by the time they reach a headline. Somewhere between Voyager 2's test results in June and whatever decision NASA has made or is currently making about Voyager 1 this July, engineers are working through exactly the kind of high-stakes, painfully patient process that has defined this mission since the very beginning, One command, 1 day long wait, one small piece of confirmed telemetry at a time. Think about what that patience has actually required. Decade after decade. The people who first designed Voyager 1 and Voyager 2 in the early 1970s built a mission they expected to last 4 years, 5 at the outside, long enough to reach Jupiter and Saturn and send back a handful of historic photographs before going quiet for good. Nobody on that original design team could have reasonably planned for a scenario in which their spacecraft were still operational, still returning usable data, closing in on their 50th year in space, forcing an entirely new generation of engineers, some of whom were not yet born when Voyager launched, to invent an entirely new kind of fix, simply because the old fixes had all already been used. The Big Bang did not exist as a concept when this mission began. It exists now because a machine built for a 4-year assignment refused, again and again, to actually stop working on schedule. And every additional year it survives forces the people managing it to solve problems nobody budgeted time or expertise for in 1977. Whether the Big Bang succeeds, buying both spacecraft more time and possibly bringing LECP back online, or whether it fails and the mission's slow, steady decline continues exactly as engineers have long expected, the answer is out there right now, traveling back toward Earth at the speed of light, simply waiting for enough hours to pass for us to actually hear it. And even in the failure scenario, it is worth remembering that failure here does not mean silence tomorrow. Both spacecraft would simply continue along the slower, more familiar decline that has defined the last several years of this mission. Instruments going dark one at a time, power dropping 4 watts a year. For however many more years, the remaining generators can sustain at least a heartbeat signal back to Earth. There's something worth holding on to in the fact that we are still, right now, in the summer of 2026, waiting to find out. Not reading about a discovery that already happened years ago and is only now reaching headlines. Waiting in something close to real time on a decision being carried out by radio signal across a gulf of space so vast that the answer is already decided somewhere out past the edge of everything we can currently see and simply has not gotten here yet. If this is the kind of story you want more of, subscribe and check back for updates, because this particular chapter of the Voyager mission is still being written in real time.